Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about long-term impact of rider experiences. This episode is based on a tech blog titled My Starter Project on the Lyft Rider Data Science Team. Throughout this episode, we will explore this topic from both a business and technology perspectives. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Lyft is one of the two largest ride-sharing platforms in the United States. The company generates roughly $6 billion in annual revenue and serves more than 50 million active riders. In such a competitive market, retaining riders is one of Lyft's highest priorities, and that ultimately comes down to delivering a consistently great rider experience. Every trip is made up of many small moments that shape how a rider feels about the platform. How long did they wait for a driver? Did the driver arrive quickly? Was the route smooth? Did the ride end without any unexpected issues? Individually, these moments may seem minor, but together they influence whether a rider chooses Lyft against the next time they need a ride. Naturally, this leads to an important business question. Which parts of the rider experience actually drive long-term retention? Answering that question is much harder than it first appears. It is relatively straightforward to measure whether a rider enjoyed a particular trip through ratings or surveys. But what Lyft really wanted to understand was causality. For example, if a rider experiences a faster pickup today, does that actually cause them to take more rides over the next month? If it does, how large is that effect? The answer has significant business implications. Lyft could invest in reducing pickup times, improving routing, lowering prices, or enhancing customer support. But engineering resources are always limited. Without knowing which improvements have the greatest impact on long-term retention, it's difficult to prioritize those investments effectively. What the team needed was a scientific and scalable framework that could measure the causal impact of different rider experiences and guide product decisions with confidence. Now that we've understood the business problem, let's dive into the technical side and see how the team tackled this challenge. The tool introduced is called Rider Experience Score. It estimates how specific rider experiences affect long-term rider volume, which is measured as the change in the number of rides a rider takes over the following 28 days. Most ride-sharing metrics are trip-level metrics, such as ratings, completed rides, and tips. While these metrics describe what happened during the trip, they don't tell you anything about future retention. The Rider Experience Score is designed to estimate whether an experience, such as a lower ETA, actually causes riders to take more rides over the following months. Knowing what is the objective, the next question is, how do we actually estimate the causal impact? Let's take a look at several potential approaches. One obvious approach would be to compare riders who experienced low ETAs with those who didn't, and then see who took more rides afterward. However, this naive comparison can be highly misleading because of confounding factors. Here is one example. Low ETAs tend to occur in dense urban areas where driver supply is high. Let's call this City A. In suburban areas, where there are fewer drivers, ETAs tend to be higher. Let's call this City B. However, riders in City B may actually take more rides on average because they have fewer public transportation alternatives. As a result, the raw data might show that the riders with higher ETAs take more rides overall. If we interpreted that correlation literally, we might mistakenly conclude that faster pickups hurt retention. This is a classical example of Simpson paradox, where geography acts as a confounding factor and masks the true relationship between ETA and future rider behavior. While the naive approach may not work, another possible approach would be to run an A/B test. However, A/B tests are typically conducted over relatively short periods because they consume engineering and experimentation resources. Since the company needed to measure 28 days retention effects, such experiments could take months to complete. That's both slow and expensive. And for something like ETA, which is largely determined by driver supply rather than a product feature, running an experiment may not even be possible. Given the limitations of these approaches, the team built this rider experience score using a causal inference techniques called Augmented Inverse Propensity Weighting. The name sounds intimidating, but the intuition is actually quite straightforward. Let's return to our City A and City B example. Riders don't randomly receive low ETAs. A rider's location, travel patterns, time of day, and many other factors all influence whether they receive a fast pickup. Those same factors often influence how often they ride in the future. That's exactly what creates the confounding problem. The Augmented Inverse Propensity Weighting approach addresses this challenge by combining two separate models. The first model is called propensity model. It estimates the probability that a rider receives a particular treatment, in this case, a low ETA. All of this is based on everything we know about that rider. You can think of it as answering the question, given this rider's circumstances, how likely were they to receive a fast pickup? The second model is the outcome model. Instead of predicting the treatment, it predicts the outcome. Given a rider's characteristics, how many rides would we expect them to take over the next 28 days? The algorithm then combines information from both models to estimate the causal effect of the experience. What's specifically powerful is that the two models correct for confounding in different ways. If either the propensity model or the outcome model is specified correctly, the final estimate remains unbiased. Statisticians refer to this property as double robustness. This robustness is very valuable because neither model is guaranteed to be perfect in practice. Real-world rider behavior is complex. But combining both approaches, the team can produce a more reliable estimate of how much an experience actually changes future rider retention. This data scientist's first project was to refresh this stale rider experience score estimates and expand the pipeline to include additional rider experience. The final output is a scorecard in which each experience is assigned a quantified causal impact of 28-day retention. Product teams can then use these scores to prioritize the improvements that are most likely to increase rider loyalty. Now that we've discussed both the business problem and the technical solution, let's wrap things up. In this episode, we talked about why Lyft needed to understand which rider experiences drive long-term retention. We discussed how raw observational data can produce misleading conclusions because of confounders, and how the Lyft's Rider Experience Score addresses this challenge using Augmented Inverse Propensity Weighting, which is the doubly robust causal inference method that adjusts for those confounders and produces experiment quality estimates without running an A/B test. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is very appreciated, and I'll see you next week.